Hi everyone, today we are going to break down some important concepts like the dissociation constant and pH. First, let's define what strong and weak acids are. Strong acids in aqueous solutions almost completely dissociate or entirely break down into ions, while weak acids or bases only partially dissociate in aqueous solutions. Here you see an example of a strong acid and a strong base. Hydrochloric acid almost completely dissociates into H plus ions and chlorine minus ions. And sodium hydroxide breaks down in an aqueous solution into sodium plus and OH minus ions. An example of a weak acid is acetic acid or ethanoic acid, which only partially dissociates in water into H plus ions and the acetate ion. The extent to which a weak acid or base dissociates can be characterized using the dissociation constant. This is an equilibrium constant for the electrolytic dissociation process. Let's take the dissociation of acetic acid as an example. It breaks down into the acetate ion and the H plus ion. For this process, the formula for calculating the equilibrium constant of this dissociation constant can be written as follows. K equals a ratio of the product of the concentrations of the acetate ions and the H plus ions to concentration of the undissociated ethanoic acid. As is evident from this equation, the stronger the acid or base, the more it dissociates into ions. Accordingly, the product in the numerator will be larger and thus the dissociation constant will be greater. This means we can determine the strength of an acid or base using the dissociation constant. The larger the dissociation constant, the stronger the acid or base. Moving on, water also dissociates to some extent. It partially breaks down into H plus ions and OH ions. We can write the formula for the dissociation constant for water as a ratio of the product of the concentration of H plus ions and OH minus ions and the concentration of undissociated water molecules. However, since the concentration of undissociated water molecules is very large compared to the concentration of H plus and OH minus ions, we can consider that it practically does not change during the dissociation of water. We can therefore write a constant in the denominator, because the concentration of undissociated water molecules is constant, and we can denote it as a constant. Next, we multiply both sides of the equation by this constant. On the left side, we get the product of the dissociation constant and the concentration of undissociated water molecules. On the right side, we get the product of the concentration of H plus ions and OH minus ions. If we have two constants, the dissociation constant and the constant concentration of water molecules, we can combine them into a single constant. This product of constants is an unchanging value, and we denote it as a Kw. Which is equal to the product of the concentrations of H plus and OH minus ions. Thus, the product of the concentration of these ions in water is a constant value. This value is called the ionic product of water. It always has a value of 10 in the minus 14th moles per liter. In a neutral medium, the concentration of H plus and OH minus ions are equal. To obtain 10 in the minus 14th mole per liter from such a product, the concentration of both H plus and OH minus ions must be 10 in the minus 7th mole per liter. We know that when multiplying numbers with the same base, the exponents are added. 10 in the minus 7th times 10 in the minus 7th equals 10 in the minus 7th plus minus 7th, and it equals 10 in the minus 14th. Therefore, when we multiply 10 in the minus 7th mole per liter by 10 in the minus 7th mole per liter, we get 10 in the minus 14th. Accordingly, if the concentration of H plus ions increases, the concentration of OH minus ions decreases and vice versa. And therefore, if H plus ions prevail, we have an acidic medium, and if OH minus ions prevail, it is an alkaline or basic medium. For example, suppose the concentration of H plus ions is 10 in the minus third mole per liter. Then, using the ionic product of water equation, the concentration of OH minus ions can be expressed as the ratio of the constant, the ionic product of water, to the concentration of H plus ions. We substitute the numbers and get 10 in the minus 11th mole per liter. So, at an H plus ion concentration of 10 in the minus third, OH minus ion concentration is 10 in the minus 11th mole per liter. Thus, the H plus ions prevail, and we have an acidic medium. Since it is quite inconvenient to work with such numbers raised to a power, the concept of pH was introduced. pH is the negative decimal logarithm of the H plus ion concentration. Accordingly, if we have an H plus ion concentration of 10 in the minus third, the logarithm of this number taken with the inverse sign is 3. Therefore, we have a pH of 3. In a neutral medium, the concentration of H plus ions is 10 in the minus 7th mole per liter. Therefore, the pH in this case is 7. We can use the pH value to determine the nature of the medium. If the pH is less than 7, the medium is acidic. If the pH is equal to 7, the medium is neutral. And accordingly, if the pH is greater than 7, the medium is alkaline. That's all for today. We will see you in the next videos where we will continue to examine acid-base equilibrium.